Assalamu alaikum everyone. Welcome to the course of Digital Signal Processing, lecture number 4, chapter number 2. In previous lecture, we talked about convolution. We talked about the properties of convolution, LTI system, and we also discussed about impulse responses. In today's lecture, we will talk about the frequency response and Fourier transform properties. So let's get started. So in this slide, we will talk about the eigenfunctions for LTI systems, and we will compute the formula of finding out the frequency response or the Fourier transform. So in this slide you can see that we are considering the input x of n is equal to e raised power j omega n. So here we want to demonstrate that the eigen property of complex exponential for discrete time systems, we are going to consider this as an input. So we are considering an complex exponential, and this complex exponential input is the eigenfunction, okay, where omega is in radian, which is frequency. So the corresponding output of LTI system, we know that how we can find out the output of LTI system. I am going to write here y of n is equal to, with the help of convolution, x of k h of n minus k. Everybody knows the formula of convolution. K is equal to minus infinity to infinity. So we know that the input is equal to x of n is equal to e raised power j omega n. So here, rather than having shift in impulse response, we can use the commutative property and we can replace the formula as h of k x of n minus k. K is equal to minus infinity to infinity y of n. So if I have x of n, so x of n minus k will be this thing, okay. So just having a shift of n minus k. Rest of the formula you can see that this is same. Now as the summation is applied upon k, so we can take this term outside the summation, e raised power j omega n. This term is the eigenfunction. Whenever you apply complex exponential at the input of LTI system, you can separate it, okay. So now this rest of the thing is the formula for Fourier transform or the formula for calculating the frequency response. Why I'm saying that this is formula for calculating the frequency response? Because here we have impulse response. So if we have impulse response here, we can calculate the frequency response. If we have input signal here, it means that we can calculate the Fourier transform of the input. So this is the formula for finding out the Fourier transform of impulse response. So the signal that is in time domain and then the negative phasor. So this is frequency response. If we have x of n here, we will have x e raised power j omega correspondingly, okay. So now the output is equal to frequency response into this is the input. So this is eigenfunction and this is eigenvalue, okay. This is eigenvalue. So let's move on to next slide. So consequently x, I have told you e raised power j omega is an eigenfunction of the system and the associated eigenvalue is this thing, okay. So and this eigenvalue basically describes the complex exponential, that is the complex amplitude of a complex exponential input. So this is the frequency response. So the frequency response can be break down into real part and the imaginary part, because this frequency response is complex, so it has two parts, real and imaginary. So this is basically the term which will affect the input amplitude and the phase. Now this was in rectangular form, this is in polar form, the magnitude and the phase. So two things that you need to remember here is that whenever you apply complex exponential at the input of the LTI system, you will get that complex exponential at the output multiplying with the frequency response, and frequency response will alter the amplitude and the phase of the input signal. Let's move on to next slide. So here in this example we are going to find out the frequency response of the ideal delay system. So this is the ideal delay system, everybody knows, we have discussed this many times. So what we are going to do, there are multiple ways to find out the frequency response of this system. First of all, we are just considering, let's say our input is e raised power j omega n. So if our input is this, we require x of n minus t here. It means that we have to replace this n with n minus nd. So the output is this thing. So here's the input, as I've told you that input will always appear at the output, and this is the frequency response. Okay. The other method is shown here. Okay, the other method is shown here. This is the frequency response, the rest of the part, and this part is input. The second method is that you need to find out the impulse response of this system. The impulse response of this system is delta of n minus nd. H of n is equal to delta of n minus nd. Putting in the formula, delta of n minus nd, negative exponential, and summation from minus infinity to infinity. We know that this is just a single term, and this is defined at delta of nd minus nd, because delta is only defined at 0. So it means that we have to put n is equal to nd. So we will have this output e raised power minus j omega nd. So the summation will be expanded only for n is equal to nd. Okay. So now we can find out the two parts here. The real part, we know that real part is cos, because e raised power minus j omega nd is equal to cos of omega nd minus j sine of omega nd. So cos omega nd is the real part and the imaginary part is minus sine omega nd. Whereas the magnitude, this is in polar form, this is also in polar form. So the magnitude here is 1, here is 1. So magnitude is 1 and the phase is omega nd, leaving minus j, rest of the thing is phase. So this is how you can find out the frequency response, either by putting the input is equal to complex exponential, or by finding out the impulse response and then putting out the impulse response in the formula. That is how you can find out the frequency response of the system. So let's move on to next slide. Now this equation is for a signal where we have multiple frequencies. Okay, so we can have a signal that can be represented by linear combination of complex exponentials. So this is a linear combination of complex exponential. Now we are breaking down x of n into alpha k e raised power j omega k. Previously we have seen that we have only one frequency, but what if we have like multiple frequencies in a signal? Okay, so this is for linear combination of complex exponential. It means that we have more than one complex exponential. One is e raised power j omega 1 and other is e raised power j omega 2n, and this is scaling. So if we have such thing, now the output will appear, this whole thing will appear at the output. This is alpha k, this is e raised power j omega. The only thing that I want to tell you is that whatever is the input, the response will be applied to that particular frequency. For example, if the input is e raised power j omega 1 and the response will be evaluated at e raised power j omega 1. So this is the input appeared as it is, and this is the frequency response. So from the principle of superposition, the corresponding output of a linear time invariant system is this. So whatever the input frequency is, the frequency response will be applied to that particular frequency. Let's move on to next slide. So here is an example of that system with two frequencies. Okay, so here we are going to find out the sinusoidal response of LTS system. So this is the signal x of n is equal to a cos omega naught n plus phi. So what we are going to do, we are going to expand this and represent in the form of Euler. We know that the formula for cos theta, we can expand this in Euler from 1 by 2 e raised power j theta plus 1 by 2 e raised power j theta. This is the formula. So this is a by 2 because here the magnitude is a by 2, and then we have e raised power j phi because of this e raised power j omega naught n. So this is basically just like this. If I take j common, we will be left with omega naught n plus phi. So this is the same thing. We can write this. I can write this e raised power j omega naught n dot e raised power j phi. So this is just the expansion of this equation. Now we know that input here is this one. X1 is this and X2 is this. So let me clear this out for you. So this is our first input and this is our second input. So this is X1, this is X2. Okay. So now for X1, you can see that the frequency is omega naught. So the frequency response here will be e raised power j omega naught. In second one, the input is e raised power minus j omega naught n. So the frequency response will be minus j omega naught n. So we just assume that the frequency response for this will be e raised power j omega naught. The second one minus j omega naught. This is y1, this is y2. If we add them, we will have total response. So substituting the value of y1, substituting the value of y2, and then we know that these are conjugate of each other. One is e raised power j omega naught, so the conjugate of e raised power j omega naught will be e raised power minus j omega naught. So what we can do, these two are conjugate of each other. Okay. So these two are equal, so this will become 2 times e raised power j omega naught and e raised power j omega naught. So 2 will be cancelled and we will left with e raised power j omega naught. Okay, and the rest of the thing, this term plus this term, this will be cos omega naught n phi plus theta. Okay, now theta is just the phase response of the system. Okay, so the magnitude, we know that the magnitude of this system is 1 and the phase is minus omega naught nd. This is for the previous question. We have seen that the magnitude response of ideal delay system was 1 and the phase was minus omega naught nd. So if I substitute here the frequency response, this will become 1 and here I can put minus omega naught nd. So it means that for this particular example, the system is ideal delay system. So here we have used the magnitude response of ideal delay system and so this is the final term. Okay, so only thing you need to consider is that these two are conjugate of each other, and simplifying this will become magnitude of e raised power j omega naught. Okay, so let's move on to next slide. Now in this slide we will talk about the periodicity of the response of discrete time system. So the frequency response of LTS system is essentially the same as for continuous time. So the frequency response for continuous time and discrete time is almost same. However, an important distinction arises between the frequency response of a discrete LTS system is always periodic. As I've told you that the response of discrete time system is always periodic with the period omega plus 2 pi. If I add 2 pi in the frequency, the response is going to be same. So this is the formula for frequency response. We are just adding 2 pi. This is summation, this is impulse response, and here we had previously e raised power minus j omega n. So we are adding omega plus 2 pi. So we know that if I solve for this e raised power j omega 2 pi n, if I take the value of n to be 0, it become 1. In fact, it becomes 1 for any integer value of n. So it means that if I just simplify this, this become e raised power minus j omega n. This quantity always go to 1. So we are left with e raised power minus j omega n. It means that frequency response of plus 2 pi or e raised power j omega is same. Okay. So for any integer value of, like, we can use 2 pi, we can use 4 pi, we can use 6 pi. For any integer value of r, the frequency response is equivalent to e raised power j omega. So we can say that frequency response of a discrete system is periodic with period 2 pi. So this is obviously true for ideal delay system. Okay, so the frequency response of the ideal delay system was e raised power minus j omega nd. So even if I add 2 pi in omega, this will remain same. So only thing you need to remember is that the frequency response of a discrete system is always periodic with period 2 pi. Move on. So in this slide we will talk about ideal frequency selective filters. Ideal frequency selective filter is another important type of LTS system. Why we call them ideal frequency selective filter? Because in passband their magnitude is 1, in stopband their magnitude is 0. And because the frequency response is periodic, so you will see at 2 pi or minus 2 pi, we are going to get again the same thing. So this is for multiple period, this is for single period. It means that from minus omega c to omega c, whatever frequency comes in between this range, it will pass without any distortion in the magnitude response. Okay. Whereas if the frequency becomes greater than omega c or less than minus omega c, it will be discarded. It will not appear at the output because this is stop band. This is stop band. So in ideal frequency selective filter, the pass band has a magnitude of 1, the stop band has a magnitude of 0. So this is low pass filter with periodicity. This is low pass filter for only one period. This is for one period. This is only this portion. Okay, let's move on to next slide and see some other period filters. So this filter is the opposite of previous one. It means that if I say 1 minus h low pass, if I subtract 1 from the low pass, I will get this. So this is exactly the opposite of low pass. Here we are getting magnitude response of 0. Here we are getting magnitude of 1. So that it will block lower frequency and pass high frequency. Okay, so that is high pass filter. In band pass filters we will pass bands. Okay, sorry, this is band stop filter. In band stop filter we are going to stop the bands. So between omega a and omega b we are going to block the frequencies, and between minus omega a and omega b we are going to block the frequencies. So similarly, if we subtract 1 from band stop, we will get band pass. So omega a to omega b, it will pass whatever comes in between this frequency with a magnitude of 1. So if any system has a magnitude of 1, it means that it will not affect the magnitude response of magnitude of the input signal. So here the magnitude is 1. Rest of from 0 to omega a and 0 to minus omega a, the magnitude response is 0. So these are ideal frequency selective filters: high pass, band stop, and band pass. This is going to pass this band and this band. The negative frequencies are just taken for the purpose of symmetry. That's it. Let's move on to next slide. So here we have the example of frequency response of moving average system. From our previous lecture we know that moving average system basically takes the average of impulse response between the point minus m1 and m2, and this is the frequency response, this is the impulse response of the moving average system, and which is just the average of starting point, ending point plus 1. Okay, so this is the impulse response, and we know how to find out the frequency response. We can find out the frequency response. We just have to place h of n here, negative phasor, starting point, ending point. So h of n is simply this thing, which is a constant thing, so we can take this out of the summation. Okay, now I have told you in previous lecture that this is what? This is geometric series, so you have to expand this. So the first term here will be, this is finite sum starting from minus m1 to m2. So the first term will be e raised power minus j omega, putting n is equal to minus m1. So this will become e raised power j omega m1. So the last term will be e raised power minus j omega m2 plus 1. Last term plus 1, m2 plus 1, divided by ratio. So ratio is this thing, so 1 minus ratio. Now if you see here, this term and this term, we can take something common. So we can make half angle identities here, and by taking this term common, so if you take this term common, we can have same angle here, same angle here, and what we can do, we can make this sine theta. Okay, so here e raised power j theta minus e raised power minus j theta. Only thing that is short here is divided by 2j. So we can also make this half angle e raised power j omega divided by 2 e raised power minus j omega by simple maths. So this term is becomes sine, this term becomes sine, so we can have sine omega m1 plus m2 plus 1 divided by 2, and similarly we can have sine omega by 2. So if you still have any issues in this slide, you can tell me and I can compute it for you. Okay, so it is just simple mathematics. All you need to do is to know that this is the impulse response, this is the impulse response, and you have to use the Fourier transform formula, and this is the formula. Here h of n was here initially, but because h of n, this term is constant, so we have taken out this term here. Okay, so rest is simple. Now if you want to plot this out, we can see this in next slide. So here we have drawn the frequency response. How we can draw this frequency response? By giving different values to omega. Okay, so in previous equation we have unknowns of m1 and m2. So if I put m1 0, m2 4, and I put different values of omega, for example here the omega 0, here omega is 2 pi by 5, then pi, I can draw this thing. Similarly for phase, I can choose different frequencies, and this is wrap phase. Okay, I will tell you about the wrap phase. Wrap phase is always between pi and minus pi, because beyond this the phase will become indistinguishable. Okay, so we keep the phase between minus pi and pi. So all you need to do in previous equation, you need to find out magnitude. Okay, you need to find out the equation of magnitude, and you need to find out the equation of phase, and then you can put these values. And I will give you this example to solve in MATLAB, because there you can compute it easily. So let's move on to next slide. So in this slide we will talk about the Fourier transform and inverse Fourier transform. So the formula is almost same as we have seen. Here you can see that we have Fourier transform of input, because we know that the Fourier transform is a continuous function. So if you want to convert Fourier transform to discrete signal in time domain, what you have to do, you have to integrate it from minus pi to pi with positive phasor, and because the signal was in frequency domain, so you have to integrate with respect to omega, and this 1 by 2 pi is that because we are integrating it over the period. So this formula is for inverse Fourier transform, and this formula is for Fourier transform, which we have already seen. X of n, signal in time domain, negative phasor, we will get this. If I put x of n here, I will get x e raised power j omega. Here I will get x of n. Okay, so this is simple. So let's move on to next slide. We know that we have seen that the Fourier transform of input signal is x e raised power j omega n, and in fact, because this is a complex function, so I can break into real part and imaginary part. Likewise, this is complex, I can break it into polar form, magnitude and phase. Okay, so this is rectangular representation of a Fourier transform of x of n, and this is phasor polar representation of x e raised power j omega, which is the Fourier transform of x of n. Let's move on to slide. So here you can see that this is the formula for inverse Fourier transform. We have h of n here. We have h e raised power j omega. It means the frequency response. So we want to move from frequency response to impulse response. The frequency response is given and we want to compute impulse response. So positive phasor, integrate with respect to omega and 2 pi. So just remember the first equation. This is same thing as in the previous equation, same thing. Now I'm substituting here h e raised power j omega. I know that how I can compute h e raised power j omega. What is the how I can compute this h e raised power j omega? I have told you the formula, h of n e raised power minus j omega n. N is equal to minus infinity to infinity. So same thing here, and only the variables are changed. M is equal to minus infinity to infinity, x of m, and e raised power j omega m. Now this thing is same, and d omega. Now what we are going to tell you here is that if I solve this, this is equal to x of n. Okay, because this is the formula for Fourier transform and this is the formula for inverse Fourier transform. So these two get cancelled and we get the input signal. Okay, so here we are going to solve it. X of n, which is the time domain signal, is equal to summation x of n, just rearranging the previous terms, 1 by 2 pi integration from minus pi to pi e raised power j omega. So we know that we have e raised power j omega here, we have e raised power j omega here. So taking e raised power j omega common, it will become n minus m. And solving this for integration, we know that if I compute the integration of this thing by solving it, it becomes sine pi n minus m divided by m minus m. So you can solve this integration very easily, and after solving the integration you will get this thing. So when n is equal to m, so we will get sine pi 0 by 0. So we know that sine of 0 by 0 is kind of an undefined thing. So we can use L'Hopital rule and this will become 1. And when n is not equal to m, we will always get 1. So at only one point it will become 1. So we can represent this with the help of delta function n minus m, because when n is equal to m, this will become 0 or delta of 0 is 1. So substituting delta of n minus m here in the previous equation, this is here, and here x of m, I'm just putting this equation. So x hat of n summation as it is, x of m as it is, and then we have this after solving the summation. So we know that if I multiply x of n with delta impulse, we are going to get x of n, because the impulse is defined at n. So this is the proof that if I take the inverse Fourier transform of a Fourier transform I will get ultimately the original signal. Okay, so you just need to go it through one or two times, you will understand. Now here we will talk about the convergence of the Fourier transform, determining the class of a signal that can be represented by equation in the previous slide is equivalent to considering convergence of a finite sum. So we can compute, or we can say the Fourier transform is convergent as long as the magnitude of Fourier transform is less than infinity. Okay, as long as the magnitude is less than infinity, we can compute it. So here we are using an m, and I'm going to show you how m affect the Fourier transform. So x e raised power j omega is the limit as m approaches to infinity. So this is the same formula for Fourier transform. All I'm doing that I'm not using the limit minus infinity to infinity, I'm using minus m to m. Okay, and this is the Fourier transform, this is this signal, so absolute on both sides, and we know that if I distribute the absolute, this will become less than, as I've told you in previous slide, and the magnitude of this thing is 1. So obviously if input magnitude is less than infinity, the Fourier transform magnitude will be less than infinity. So ultimately it nails down, if we have the input signal magnitude is less than infinity, the magnitude of the Fourier transform will be also less than infinity and it will converge. Okay, so here we have an example of absolute summability of sudden applied exponential. So here we have the input signal which is exponential. Okay, so this is infinite sequence. Okay, we want to compute the Fourier transform of this infinite sequence. So this is the input signal a raised power n, and then we have a negative phasor, and u of n is removed because we are using the limit from 0 to infinity. So if I take n common, it become a e raised power minus j omega n, and from 0 to infinity. So this is again geometric series with infinite sum. So for infinite sum, always this term raised to power 0. So anything raised to power 0 become 1, and 1 minus ratio. Ratio is always this argument. So 1 minus a e raised to power minus omega. So Fourier transform will converge as long as this quantity is less than 1, or we can say, because we know that e raised to power minus j omega is always equal to 1. So ultimately it means that a should be less than 1. Okay, clearly the condition a magnitude is less than 1 is the condition for absolute summability of x of n. And here we can see that we have n is equal to 0 to infinity a raised power n. So first term divided by 1 minus ratio is less than infinity as long as a is less than 1. Okay, so absolute summability is sufficient condition for existence of Fourier transform, as I've told you, and it also guarantees uniform convergence. Some sequences are not absolutely summable, so it is not necessary that all the sequences are absolutely summable. If some sequence is not absolutely summable, it may be true that their scale is absolutely summable. Okay, so here we have the example of square summability for the ideal low pass filter. The ideal low pass filter is not absolutely summable, but it is square summable. So here's the equation of low pass filter, which we have seen in previous slides, that it is 1 between the interval minus omega c and omega c. So omega mod is less than omega c mean it is 1 between omega c and minus omega c. Okay, so we have to find out the inverse of this. So we know that for finding out the inverse we have to integrate this From minus omega c to omega c, the function is 1, and this is the formula e raised power j omega. So after simplifying, we get this sine of omega c n by pi n. If I plot this omega c n, this is a sinc function. This is a sinc function. We note that h low pass, this equation, is non-zero for n less than 0. This is non-zero for n less than 0. The ideal low pass filter is non-causal. So the impulse response is non-causal. As I've told you, if impulse response exists on the negative side, it is non-causal. Also, HL pass is not absolutely similar because this is going from minus infinity to infinity. The sequence approaches to 0 as n approaches to infinity. We can see that this will become very small as n approaches to infinity, but only as 1 by n. Okay, so 1 by n, it means that 1 by infinity, which is equal to kind of 0. This is because h low pass e raised power j omega is discontinuous at omega is equal to omega c. So discontinuity means that at omega c, here you can see omega c, the value could be 0 or could be 1. So it is undefined at omega c. Since h low pass HLP, that is the response of low pass filter, is not absolutely summable. So if you sum this, this is not absolutely summable. Summing it from minus infinity to infinity, this is not absolutely summable, but it is scarce summable. Okay, so here is the frequency response, and if we take m is equal to 1, the sinc function will look like this. If I take m is equal to 3, the sinc function will look like this. If I take m is equal to 7, it will look like this. If I take m is equal to 19, it will almost become this. So it's depending upon the value of m. Okay, so at omega is equal to omega c, this is Gibbs phenomena. You can see that this is Gibbs phenomena at the omega c frequency. The spike is maximum. The spike is maximum. So here we are, this is the ideal frequency response. The scale one is ideal frequency response, and this bell shape is basically the convergence. So if m is equal to infinity, this will exactly become square. At m is equal to infinity, this will become square. So in previous slide, you can see that if I take m is equal to 1, this is just this thing. If I take m is equal to 3, we have, it is approaching to the square. At m is equal to 7, it is again getting closer. At m is equal to 19, it almost matches the square, but at m is equal to infinity, it will become pure square. So here's the few Fourier transform pairs, which you can see that if you want to find out the inverse Fourier transform of delta of omega minus omega naught, like this is an impulse in frequency domain. It means that this is an impulse in frequency domain at point omega naught. So if you want to find out the inverse, so integration from minus infinity to infinity of this signal e raised power minus j omega naught t d omega. So this is defined at omega naught. We know that this is defined at omega naught. Substituting omega is equal to omega naught, this will become 0 and this will become e raised power j omega naught t. Okay, so this will become e raised power j omega naught t and 1 by 2 pi. So 1 by 2 pi e raised power j omega naught t. It means that if I take out the Fourier transform of this, it will become this, or vice versa. If I just multiply it here, so it tells me the Fourier transform of this is this, and the Fourier transform of negative is this. It means that if you have exponential signal in time, the Fourier transform will be 2 pi magnitude, and this impulse will be at delta of omega minus omega naught. Okay, why I told you about the Fourier transform this, because later on you will see that it is most commonly used Fourier transform. Everybody knows the Fourier transform of delta of t. Delta of t Fourier transform is 1, or delta of n Fourier transform is 1. Okay, but the Fourier transform of exponential is this thing. Okay, so here the Fourier transform, we want to compute the Fourier transform of cos omega naught t. So first of all, breaking the cos omega naught t into Euler, it will become 1 by 2 e raised power j omega naught t plus e raised power minus j omega naught t. And we know that the Fourier transform of e raised power j omega naught t is 2 pi delta of omega minus omega naught. So 2 gets cancelled with 2, so we are left with pi delta of omega plus omega naught and delta of omega minus omega naught. So this is delta of omega plus omega naught, and this is delta of omega minus omega naught with amplitude pi. This signal was in time domain, this signal is in frequency domain. Okay, so now we want to compute the Fourier transform of impulse train. So this impulse train is in time domain. You can see 0 to omega 0, t naught, 2 t naught, 3 t naught. So this is periodic impulse train, and the difference between the impulses is t naught. So if I take the Fourier transform of periodic impulse train, I get periodic impulse train but in frequency domain. So 0, omega naught, 2 omega naught, 3 omega naught, minus omega naught. But the magnitude of this is, or the amplitude is omega naught delta omega naught. Okay, so the amplitude of each impulse is omega naught. Okay, so how we can compute it? This is the impulse train in time domain. We know that delta of t is simply this. Okay, then delta impulse shift, where shift? It shifts to, for example, n is 1, so it will shift to t naught. If n is minus 1, it will shift to minus t naught. Okay, so this is delta impulse, and these are getting added. So we know that we have to represent this in Fourier series because this is periodic, and for periodic sequence we need to represent this signal in the form of Fourier series. So delta of t, t naught, and this is shift, so shift is represented by e raised power j omega naught t, and then the Fourier series coefficient dn. So if you find out the Fourier series coefficient of this, it will become 1 by t naught. I am going to explain this and I am going to show you the complete derivation, but at the moment just have a look at this, that the Fourier transform, Fourier series coefficient become 1 by t naught. So just substituting 1 by t naught here, at d naught you will get, substitute this d naught here and take out the Fourier transform. So you will get 2 pi by t naught, summation will remain same, and then this exponential will change to we know that exponential will change to delta of omega minus omega naught. So this is, so these are the impulses in frequency domain, and this is the height of the impulses. So we know that 2 pi by t naught is equal to omega naught, so that's why we are using omega naught here. Okay, so three things we learned here, that the Fourier transform of impulse is 1, whereas the Fourier transform of exponential is impulse with amplitude of 2 pi. And the last thing we studied here is that the Fourier transform of impulse train is impulse train but in frequency domain with a amplitude of omega naught. So these are the symmetric properties of Fourier transform, which you can see here. If we have x of n signal with conjugate, the Fourier transform will have a conjugate. If I have x of n conjugate with x of n flipped, we will have x conjugate e raised power j omega. So you don't need to compute the Fourier transform of every signal. Like if we have compute the Fourier transform of x of n, you can also compute the Fourier transform of x conjugate e, sorry, you can compute the Fourier transform of x conjugate minus n. So we know that the Fourier transform of this is x e raised power j omega. So the Fourier transform for this will be x e raised power j omega conjugate. So the real of x of n means that the even portion in the e raised Fourier transform. Imaginary of x of n means the odd portion in Fourier transform. Even of the signal means that the real portion of Fourier transform. Odd means the imaginary portion of the Fourier transform. And if x of n is real, these hold. X of n Fourier transform will be equal to its conjugate symmetric. If x of n is real, we know that in real signal, the left and right side are equal. If x of n is real, the odd side are one is positive and other is negative. For example, we have a sinusoidal signal. If you see that the sinusoidal signal, one side is negative, the other side is positive. And finally, if x of n is real, so magnitude is even. It means the magnitude of left and right side are equal. Whereas for any real signal, the phase is odd. Okay, the phases of one side is, if phase of one side is 90, the other side will be minus 90. The even part is real and the odd part is imaginary. So these are the symmetric properties that you must need to understand and solve. And for example, we have a question here. We know that the Fourier transform of this signal is this. We have computed this in previous slide. Now, if you want to find out we know that this is real signal. So for real signal, x e raised power j omega is equal to x conjugate e raised power minus j omega according to the property 7. So if you want to find out the real, here in this we have real and imaginary. So how we can find out real? You can use property 8 and you can take complex conjugate of this equation to find out the real. And for imaginary, you can take the complex conjugate. So if you multiply x e raised power j omega with x e raised power minus j omega, you will get real terms and you will get imaginary terms. Okay, so the real terms are these and the leftover imaginary terms are these. Okay, and if you take the magnitude of real plus imaginary, you will get this thing. Okay, that's the magnitude. And if you find out the phase, that is tangent inverse of imaginary divided by real, you will get this equation. Okay, so you need to practice this out yourself. All you need to do is to take the complex conjugate of this equation where property 7 is written. So you can find out the real, imaginary, magnitude and the phase. Let's move on to the next slide. So these are the plots of the previous question. So here in first figure, frequency response of the system with impulse response, this real part A was greater than 0. Here in solid 1, A is 0.9, in the dash 1 A is 0.5, and this is the magnitude and this is the real part and this is the imaginary part. Okay, in imaginary part, this solid line represents A value of 0.9, whereas this dotted line represents A value of 0.5. So you can see that this is odd function because here we have positive value, here we have negative values, and this is even function. We have same values here and we have same values here on the left or right side of the 0. Okay, so magnitude A greater than 0, a equal to 0.9 and a is equal to, so here we are, this is the magnitude and this is the phase, okay, for two values of a, 0.9 and 0.5. So this was the real part and this was the imaginary part. And these are the Fourier transform theorems. So if the Fourier transform of x of n is this, x e raised power j omega, and Fourier transform of y of n is this, so if there is a scaling at x of n, we will have scaling with the Fourier transform. We have scaling with y, we will have scaling with the Fourier transform y. We know that if we had a shifting in the signal, we will have a complex exponential. So how much shifting? Minus nd, so we will have e raised power minus omega nt. If we have complex exponential in time domain multiplying with signal, what we will have? Our Fourier transform will be shifted to minus omega naught. Now the frequency will not be, it will not be x e raised power j omega. It will become x of e raised power j omega minus omega naught. If we have flip signal, the Fourier transform will become flip, okay, or we can simply say x conjugate only if x of n is real. If there is a running variable multiplying with x of n, the Fourier transform will be the, first we will take the Fourier transform of x of n, which will be this thing. Then we will derivate the Fourier transform, multiply with j, it will be the Fourier transform of this nx of n. If there are convolution in time domain, there will be multiplication in frequency domain. If there is multiplication in time domain, there will be convolution in frequency domain. This is Parseval theorem. This is, we know that if we scale these samples and add them, this means that we are finding out the energy. So finding out the energy in time domain is equivalent to scaling this Fourier transform and taking out its integral. The energy will be same in frequency domain and time domain. And here we have x of n multiplying with what? Y of n conjugate, and this is equivalent to Fourier transform of x of e raised power j omega multiplying with Fourier transform of x e raised power j omega. So this is Parseval theorem. It means that if we find out the energy in time domain, this is equivalent to finding out the energy in frequency domain. So these are same things. Here we have two signals, x of n, y of n. Here we just have one signal. So here we have another example in which we are going to apply some properties from the table. So this is the signal, and we know that the Fourier transform of this signal is 1 divided by 1 minus a e raised power j omega. Now if you want to shift it, we want to find out the Fourier transform of x of n minus 5. It means that if you need to shift it, it means that for shifting you just need to multiply this with e raised power minus 5 j omega, okay, and then there is a scaling. So if we have a scaling of a5, you need to multiply a5. So ultimately we find out the Fourier transform of x of n a raised power n u of n. So we started out with this thing that we know the Fourier transform of x of n is equal to a raised power n u of n, which we have computed before. So first we find out this, then we find out the Fourier transform of a raised power n minus 5 u of n minus 5. So it means that there is a shifting of how much? Shifting of n minus 5. So for n minus 5 we need to multiply exponential as per property, and then we don't require a n minus 5, we require a n. So it means that we have to multiply this with a raised power 5, okay, so a raised power 5. So these are the properties. You can go through the text and can read out. Let's move on next slide. So here we want to find out the inverse Fourier transform. So you see that we have a Fourier transform in rational form, p by q form. So whenever we have such kind of a Fourier transform, what we have to do, we have to apply partial fractions. Okay, so what we did, we can write this a divided by this term plus b divided by this second term. Okay, so we can find out the values of a and b. This is the value of a, this is the value of b, and now I can take the inverse. This is scaling, this is just the scaling, so scaling become at the output. And we know that what is the inverse of this? The inverse of this is a raised power n u of n. This is scaling, and we know the inverse of this 1 divided by 1 minus b e raised power j omega. The inverse of this is b raised power n u of n. So you need to know where to apply the partial fraction. We apply partial fraction to find out the inverse. So we just convert this multiplication into addition or subtraction, and then finding out the inverse Fourier transform. Moving on to next slide. Here we have 1, and we want to find out the impulse response from the frequency response. This is the frequency response of high pass filter. How I get to know this is high pass filter? From the limit. The limit says that from omega c to pi, this is magnitude is 1 because e is multiplying with 1, and from minus omega c to minus pi because this is mod. Okay, so this is high pass filter. It is not passing the low frequency, it's passing the only high frequency. So we have to find out the inverse. So I am going to use the property here. I know that the relationship between the high pass filter and low pass filter is this: 1 minus low pass filter is basically high pass, and this is just the phase. Okay, so this is multiplying 1 minus low pass is equal to high pass. So simplifying this, multiplying e raised power minus omega n d with this and this. So we know that if I take the inverse of this, so if there is shifting if there is an exponential in frequency domain, its inverse will be delta of n minus t. And we know that the impulse response of low pass filter is sinc. The impulse response is sinc. So sinc is sine of omega c divided by pi n. But because we have a shifting here, so we will have omega c n minus nd and n minus nd. So this is the impulse response. So let me again recap it for you. So the frequency response of a high pass filter was given to us, and the frequency response of high pass filter was shifted. So we know that the relationship between high pass and low pass filter. So we said high pass filter is equal to 1 minus low pass filter and the shifted response. Now we have high pass filter shifted response is equal to this. We are applying the inverse Fourier transform. So this shifting, this thing, the impulse response of high pass filter, we know that low pass filter is sine. We have done this in previous slides. So only thing is that there was shifting. So wherever we have n, we have to replace n with n minus nd, n minus nd. Moving on next slide. So we can represent system in many variety of ways. You know that we can represent system in impulse response form. We can represent system with the help of linear constant coefficient difference equation, and we can represent system in frequency response. So here we have to determine the impulse response for difference equation. So this is a difference equation. We have to apply impulse response. So here we are just going to replace output with impulse response and input with impulse response. Now we can apply Fourier transform. So the Fourier transform of h of n is generalized h e raised power j omega, and the Fourier transform of 1 by 2 scaling, and then there is a shifting h of n minus 1. So we have a complex exponential with h e raised power j omega. The Fourier transform of delta of n is 1, and then we have 1 by 4 scaling. The Fourier transform of delta of n is 1, but we have shifting here, so e raised power minus j omega. Taking common h e raised power j omega, we get this equation. Okay, so this is the frequency response, but what we are required? We require the impulse response. So now what we did, we separate the previous equation, p by q minus p by q. We know the Fourier transform, we know the inverse Fourier of this. The inverse Fourier of this is this equation, 1 by 2 n u of n, and we know the inverse Fourier of this. The inverse Fourier of this is the same thing, 1 by 2 u of n, but because of this e raised power minus j omega, we have shifting in u of n, and we have, wherever we have n, we have to replace the n with u of n minus 1. Previously we have n and same things. The only thing we have in numerator was 1 by 4 e raised power minus j omega. So this e raised power minus j omega is basically shifting in time. So we have to replace n with n minus 1, and then this is just the scaling. So the inverse Fourier transform of this will be h of n, which will be the impulse response, 1 by 2 raised power n u of n, 1 by 2 raised power n minus 1, u of n minus 1, and 1 by 4 scaling. So that was all about the Fourier transform, frequency response, Fourier transform properties. So what you need to do, you need to spend some time on it, try to solve these slides yourself, so everything will be easier for you. If you still have any question, you can ask me in the class. Thank you very much.